technical problem, but I think now it's sorted out. Let's start our class now. What we are going to do, we are going to just quickly go through what we did yesterday, because I can see that most of you could not join us yesterday. And then after that, we will be doing completely different exercises from the ones that we did yesterday, so that every one of us can benefit. And those of you who have missed yesterday's class, you can always go to YouTube and watch the video again and look at the exercises that we did yesterday. But as it is for today, we'll just go through the content, the concepts, the principles that you need to remember, and keep ourselves busy with the activities so that you can understand what is expected of you. Right. Welcome to this session. It's Physical Science Grade 11. And then I'm Musala Liburu. I'll be the presenter for today. And then my Twitter handle is @MusalaDL. And then you can also get me on Instagram. Is post_silicon. Right. We will be looking at, again, ideal gases and thermal properties. And then we'll also be looking at motion of particles, that is kinetic molecular theory or kinetic theory of gases. Right, at the end of this lesson, you should be able to understand the kinetic theory of gases and use it to explain various scenarios. And then you must be in a position to describe the motion of individual molecules. And you should be able to describe what an ideal gas is. And then you must be able to explain why real gases deviate from the behavior of ideal gas at high pressure and low temperatures. Furthermore, you should be able to state the condition under which real gases approach the ideal gas behavior. Right, let's look at kinetic theory of gases. The kinetic theory of gases is a model that is used to describe the behavior of gases. That is, it's just a model that has been used to describe the behavior of gases, of how gases behave. Right, it is used to explain macroscopic properties of gas, such as pressure and temperature. So, as well as microscopic components such as atoms. So here, what do we mean by macroscopic? Macro, we mean larger things, bigger things, and we're referring to pressure and temperature, that in which you can see pressure change, and you can be able to detect if there's pressure change and also if there's temperature change. And microscopic, meaning minute, very small components of gases such as atoms. So we are using the kinetic molecular theory to be able to explain this. All right, we are also using this theory to describe motion of individual gas molecules. And then we are also describing an ideal gas. How does it behave? We describe it, so we'll be able to describe it at the end of this lesson. So let's look at motion of individual gas molecule. So here, molecules are, you must remember that molecules are in constant motion, and as a result of that, because they are in motion, they will collide with each other and the walls of a container. Remember that if in the cars, for them to collide, one of them must be in motion. So if they are stationary, they cannot collide. So is the molecules, because they are in constant motion, they will collide with each other and the side of the walls of the container. And then for this gas molecule, there are forces of attractions between the molecules themselves. And then molecules in a gas move at different speeds. So meaning that because they are, remember they will behave because they are the molecules of the same gas, they will have the same mass. But because they are moving at different speeds, it means their velocities are different. So as a result of that, they will be having different kinetic energy. So this brings us to the fact that temperature will be a measure of average kinetic energy of molecules. So it will be an average, meaning that we will say, for instance, if one molecule is having 2, the other one is having 4, the other one is having 6. We'll add them together and divide them by 3, which is their number, and we'll be getting an average of 4, for argument's sake. So temperature is simply the measure of average kinetic energy of molecules. Right, let's continue. An ideal gas is a gas that has identical particles, and these particles occupy no volume. That is, they have 0 volume. And then these particles, they have no intermolecular forces. There is no intermolecular forces between the particles of an ideal gas. Right. And then in all collisions of molecules with themselves or with the walls of the container, there's no energy no kinetic energy that is lost. We mean that we are saying that the collisions are perfectly elastic. So all the collisions of molecules with themselves or with the walls of the container are perfectly elastic. What do we mean by perfectly elastic? We simply mean that there's no loss of kinetic energy during these collisions. Right. Remember that the real gas will deviate from the behavior of ideal gas at high pressure and low temperatures. At higher pressures and low temperature, the real gas will deviate from the behavior of ideal gas. Right, let's look at this particular diagram here. If we are having the green as an ideal gas, you will see that at higher pressure, they will occupy the volume of a real gas will be higher than that of an ideal gas. They will deviate from an ideal gas. Right, and you must remember that real gas has volume at higher pressure. So real gas at higher pressure, as I've said, they've got a volume, they occupy a volume. So it means they can be compressed further at higher pressure. So they are in a position to overcome intermolecular forces. So as a result of that, they are far from each other and they occupy a specific volume. They've got volume. Right, at lower temperature, we have also said that they deviate from ideal gas behavior at higher pressure and low temperature. Now, how do you explain this at lower temperature? At lower temperature, remember that we have said that temperature is a measure of average kinetic energy of molecules. What does that mean? It simply means if the temperature is low, the average kinetic energy of molecules is also low. So that simply means that the molecules will move slower and then therefore they can overcome intermolecular forces. So as a result of that, because they can't be able to overcome intermolecular forces, the gas will liquefy, meaning that the intermolecular forces will play a role, will be more effective at lower temperature. Why? Is because the gases, the kinetic energy of the molecules the average kinetic energy of molecules is very low. So if it's very low, it means the gases are having lower mobility, they move slower. So they can't be in a position, they don't have even enough energy to overcome intermolecular forces. So as a result of that, they will liquefy. I can see that somebody's raising their hand. Will request you to text your question so that I can respond to your, so that Milani can read the question out so that I will be in a position to respond to the question later on. Thank you.
Thanks for having to interrupt you. Mr. Musada, just give me a moment quickly. I apologize for having to interrupt you. I understand that there's a few guys in the comments that's actually just spamming this post. I'm removing all of them now. So if everybody can just please stop spamming the post. I understand that there's people that's making problems. I am removing them at the moment. Just calm down so that Sir can continue with the lesson, okay?
All right.
Thanks.
Okay, if there's anything, you feel free to stop me. Okay. All right. So remember that we have said that pressure will be a measure of collision between molecules and the size of the container. So let's carry on and look at ideal gases law. So here we've got three main laws. That is, you should, at the end of this day, you should be able to state them. That is Boyles Law, Chancellors Law, Chancellors Law, both in words and also in using mathematical expression or symbols. Right, for each of the above relationship, that is for each of one of these laws, you should be able to interpret a table of results or a graph. You should also be in a position to draw from the graph, draw a graph from given results. And you should be also be able to solve problem using a relevant equation. You must use kinetic theory of gases to explain the gas law. And then you must be able to use a general gas equation to solve problems. And then also you must use ideal gas equation, that is PV equals to nRT to solve problems. And then also remember here, we're using capital letter T for temperature. Means it is temperature in Kelvin scale. So what does that mean? It's simply that when practically we measure temperature in degrees Celsius. So you must always be in a position to convert that degrees Celsius to Kelvin scale, and also to move from Kelvin scale and convert it to degrees Celsius. Right, so Boyles law, it says that the pressure of an enclosed gas is inversely proportional to the volume it occupies at constant temperature. So pressure is inversely proportional to the volume at whenever T is constant. Therefore, we can write this as P1 V1 equals to P2 V2, right? And then we have said that this is happening at a constant temperature. Now, if we are having this kind of data where we have measured volume and pressure of a specific gas, and we are plotting the volume against the pressure, this is the pressure against the volume. This is the type of graph that we will be having. So it will be showing the inverse relation. But if we go on and take the inverse of the pressure or the inverse of the pressure or the inverse of the volume, you will be getting a straight line graph. So you should, if you are plotting this, you should be expecting a straight line graph. Although in this particular one, when I was using this data, I could not get to a straight line graph. You can see the red here. But the expected shape is the one that is drawn in blue. Right, Chancellors Law. Chancellors Law, it says that the volume of an enclosed gas is directly proportional to its Kelvin temperature, provided the pressure is kept constant. So the volume of an enclosed gas is directly proportional to temperature in Kelvin scale, provided the pressure is kept constant. Right, so it means V is directly proportional to temperature, and therefore we can say V1 over T1 equals to V2 over T2. All right, I can see another hand. If maybe we can text instead of raising the hand, Melanie will talk to me. Thank you. And then we can have temperature, volume, and then this temperature, remember that I've said that it must be converted to Kelvin scale. So converting this to Kelvin scale, you have to add 273 to the value of your temperature in Celsius degrees, in degrees Celsius. So here you'll be having -1 plus 273 will give you 272, and then -32 plus 273 will give you 241, and then -67 plus 273 will give you 206. So here you are converting it to Kelvin scale, and when you plot the graph of temperature versus volume, this is the kind of graph that you should be, the yellow one indicates the shape that we should be getting, but with this data, this is what I came to. Right, and then let's carry on and say the pressure of if we look at Boyles law, it says that the pressure of a gas is directly proportional to its temperature in Kelvin, provided at constant volume, provided the volume is kept constant. So here, in other words, it means T is directly proportional to the pressure. And then what does that mean? It simply means P1 over T1 equals to P2 over T2, where V is kept constant. All right, we'll do the same, convert the temperature from degrees Celsius to Kelvin scale, and then we'll plot a graph of pressure versus temperature, and this is the kind of graph that you should be getting. Right. Right. Yesterday we said also you must be able to use the general gas equation, that is P1 V1 over T1 equals to T2 V2 over T2. And you must be able to use this to solve problems. Right. Please, I'm urging you, all of you, maybe those of you have just joined. If there's any question, please text so that Milan can read the question to me. So
there being too many spammers joining this Zoom link the whole time. I have blocked all of them from the session, but I'm scared that there's more that's going to join. So I'll open the chats, but as soon as people start spamming the chats again, I'm disabling the chats again, okay?
All right. Okay, I will hear from you if you deem it necessary that
Perfect.
you communicate with me. Okay, sorry about that. So now an ideal gas equation is being given by PV equals to nRT, and this you should be able to use this to solve problems. And then in this particular equation, you must know that P is pressure, and then V is volume, and then N is representing the number of moles, and then R is representing the molar gas constant, which is 8.31 joule per Kelvin per mole. Yes, I've said that you should be able to convert temperature in degrees Celsius to Kelvin for use in an ideal and general gas equations. So now, remember, temperature is a measure of average kinetic energy of molecules, and also pressure exerted by a gas in a container will be a measure of collision of molecules with the walls of the container and even among themselves. All right, now for the next few minutes, that is up to up to 11:30, 30, you should try this activity on the screen.
Your questions was, how can you get the pressure again?
Come again?
How can you get the pressure again? Tamarin, maybe just elaborate a little bit on your question so that we understand in what sense you're talking of here. The next question was, so I don't understand as to why these calculations are done.
Okay.
The next question is, I'm not understanding what is being said by Sir Mosada. Prashani, you'll have to look at yesterday's lesson as well and just maybe rewatch this one if you're a bit lost. And then the last question is, what is the Kelvin temperature?
All right. Calculations. Why do we do calculations? For instance, let's look at this one maybe that we are having here. You would like to know, for instance, let's talk about for a tire, for instance, of a car. You would know that how much pressure can you maybe apply to that tire for it to burst, things like that. And also we're doing this calculation to be able to know that probably at what temperature will that tire burst, things like that. So we are able to, so that we can predict the behavior of gases. So that is why we are doing all this sort of calculations. And on the issue of Kelvin scale, Kelvin temperature, temperature normally with a lab thermometer, it is measured in degrees Celsius. So now degrees Celsius is one scale of measuring temperature. But if we are to talk about standard temperature, most of the time when we are talking about gas in gas law, we are using Kelvin scale. So what is the relationship between degrees and Kelvin scale? Is that when we are having, for argument's sake, if we are having 0 degrees Celsius, 0 degrees will be equals to 0 plus 273, and it will give you 273 Kelvin. Say you are having room temperature, which is 25 degrees Celsius. If we are to convert that 25 degrees Celsius to Kelvin scale, it means that you will be adding 273 to that 25 degrees. Then it should give you 298 Kelvin. That is the relationship between degrees, temperature in degrees and in Kelvin scale. So for like in gas equation, we are saying PV equals to M R, and T is a capital T there. So being a capital T, it means it is temperature in Kelvin scale. So meaning that if we are using calculations, if we are using this equation in calculations, you have to convert your temperature from degrees Celsius to Kelvin scale, because in here it is in Kelvin scale, which is capital T. I think that will assist you. Okay, let's try to look at the solutions here. The first question is that, okay, let's just read the opening statement. It says, Chancellors Law describes the relationship between the volume and the temperature of an enclosed gas, of an enclosed mass of gas at constant temperature. The volume of a gas at different temperatures at constant pressures are given in a table below. Right, there's a table. And then 4.1.1 is explain Charles' law in terms of kinetic molecular theory of gases. So let's try to explain this. It will be when the temperature of gas decreases, the average speed of particles also decreases. That is, the number of collision decreases and the volume also decreases. So now let's put it the other way around. The other way around, it should read that when temperature of a gas is increased, the average speed of particles also increase. So meaning that the molecules will collide with the side of the walls of the container more often with greater impact. Remember, if they are moving faster, the collision will be occurring much more frequent and also with greater impact. And then this collision will push back the walls of the container so that the gas can occupy a greater volume. So if you increase the temperature, it means you are increasing the average speed of particles. So as a result of that, molecules will move faster and then start to collide with the walls of the container. And then in the process, they will push the walls of the container back and occupy more volume than it was in the beginning. And the other question was, draw a graph of volume versus temperature at constant pressure on the attached graph. So even here, you do not necessarily have to use a graph, but you are encouraged to use a graph whenever it's provided. Let's see how will the graph look like. So the graph will be looking like this. So we know that the volume is directly proportional to the temperature. So this is what the kind of graph that you will be having. And the next question was to extrapolate the graph, that is, extend the graph and state at what temperature the graph intersects with the x-axis. And then the other question is, what is significant about this temperature? So let's now look at the graph. Right. If the graph was ending here, now if we have extrapolated until it touches the x-axis, that is the axis with temperature. So you would see that it will be touching it at this temperature, and this temperature is minus 273. So minus 273 is 0 Kelvin. So 0 Kelvin is absolute zero. So the significance of this is that it is absolute zero. Particles are no more having energy. They stick together because they've got lower energy. The intermolecular forces play a larger role. So the intercept is minus 273 degrees Celsius. It is in degrees Celsius. So when you convert to Kelvin scale, you add 273 and you'll be getting 0 Kelvin. Right, let's carry on. And the next, other question was, sorry about that. Okay. The other question was, okay, we have answered this one, that the significance of this value is that it is zero, it is absolute zero, where particles are no more moving. Now you have to calculate the volume that this gas will occupy at 120 degrees Celsius at constant pressure. And the last question is, The experiment is now conducted at lower constant pressure. On the graph that was drawn in 412, sketch the graph that will be obtained at lower pressure. Label this graph P. So let's carry on. Right, we have talked about the significance of this intercept, that it is absolute zero, which is the coldest possible temperature. So particles will no more move as they will have no kinetic energy. Now we are to calculate the volume at the temperature. At what temperature was it? We're told to calculate the temperature, sorry, the volume at 120 degrees. So calculating the volume at 120 degrees. So now remember that what is 120 degrees? You are having the volume here, which is at 120 degrees in terms of the volume here at 120 degrees is still unknown. So that's what we are looking for. So here you are saying you substitute this, and then after that you then say look for V2, which is at 120 degrees. What is that we know? We know that at 120 degrees, it will be 120 plus 273. It will give you 393. So where is the 155 and the 373 coming from? Let's go back to our data. Sorry. Looking at our data, we are having a volumes here. Say if we are having 155 and then your temperature is 100, to convert the 100 to Kelvin scale, you have to add 273. So it will give you 373. So that is where these values are coming from. So it will be 155 plus 373 temperature. This will be the volume, and then you will then, there's V2 is unknown, then V2 will be equals to 163.31 if you calculate it here. And then now the question was, how will the graph look like if this experiment was carried at lower pressure? At lower pressure, what did we say? We said normally real gas will deviate from ideal gas. So they will have a higher volume, meaning that you will have a steeper line now. This is your P, which will be more steeper. If this, remember the blue one is when this experiment is carried at higher pressure. So so here you are having it, if it's now carried at a little bit of higher pressure, now you will have this occupying, the gas occupying more volume. So let's try out this one here for the next 5 minutes. Right. An unknown gas with a mass of 0.77 gram occupies a volume of 0.32 cubic decimeter at a temperature of 27 degrees Celsius and a pressure of 96 Kelvin. Assume that the gas behaves as ideal gas. So this gas is having this mass and then it occupies this volume at 27 degrees and is having a pressure of 96 Kelvin. Assume that the gas behaves as an ideal gas. What is the molar mass of this gas? Now, for us to get molar mass of the gas, the first thing that we need to get is the number of moles that are there. So we know that PV equals to nRT. So P it is 96 and kilo is 1,000, which can be represented by 10 to the power 3. So it is 96 times 10 to the power 3. And the volume here is 0.32 times 10 to the power minus 3. You are converting this to cubic meters. So this is what you are getting here. And then N is the number of moles. And then this is what we are looking for. R will be the general gas constant. And then temperature is 27. So I've said that you should be working always in Kelvin scale. So to move from degrees Celsius to Kelvin scale, you have to add 273. So you have to say 27 plus 273 is 300. So it is this where the 300 is coming from. And then you'll be getting your N to be 0.12 mole. And then the number of moles would be equal to mass over molar mass. So we want to the molar mass of this gas. So this is the number of moles, this is the mass of the gas, and then molar mass is what we were looking for. So we would substitute and then cross multiply, and we would get our molar mass to be 64.17 gram per mole. And then the question is, after this, write the molecular formula or the name of this gas. Now, we would go and look for a gas with this molecular mass. So we'll then find that it is sulfur dioxide. So sulfur dioxide, it is our gas. Right. Tomorrow we'll try to start with this particular exercise, but I think you can be in a position, I'm not sure how many minutes we are left with. I think we'll start with this exercise and take it from there. All right, let's carry on. What you need to do is to remember the definition of concept discussed in this session. You must be able to do calculation of ideal gases law. You must be able to please use previous DB question papers to revise and remember to practice. And then where you need help, please ask for help. You can also use this link to get more resources. And then I hope that we have gained something from this exercise. Let's meet tomorrow. We'll look at that particular exercise that I projected and then look at quantitative aspect of molecular change. And then you can always email me at mosala.liburu@gmail.com. And also on social media, I'm on Twitter, it's @mosaladl, and on Instagram is pose_silicon. Thank you. See you tomorrow.